Channel Science Icon. Today's lecture is Euler's formula. The Euler's formula of a complex number is important enough to be deserve a separate section. It is an extremely convenient representation that leads to specification in a lot of calculation. Euler formulas in a complex analysis is used to establishing the relationship between trigonometry and function, trigonometry function and complex exponential functions. Euler formula is defined and from any real number x is written as e to the power I ex equals to cos x plus I sin x. Here cos x and sin x are trigonometric functions, and I is the imaginary unit and e is the base of a natural logarithm. The interpretation of this formula can be taken in a complex plane as a unit of complex function and e to the power I theta. Tracing any unit circle where theta is a real number to measure the radius of the circle. This representation might seem confusing. At first, what sense does it make to raise a real number to an imaginary number? However, you may rest assured that a valid justification for a relation exists, although we will not discuss the reason proof for this. You may observe the following approximate proof to see why should be true. We use the following expansion series of e to the power x. E to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial, and it's so on to infinity. Now we assume that this expansion holds true if x is non-real number in the Regenus proof. Even this assumption and with have to be justified, but from now let us take the truth to be granted and use as x equals to I theta. Then it expression written as e to the power I theta equals to 1 plus as I theta plus I square theta square by 2 factorial plus I cube theta cube by 3 factorial to infinity. As we know that I square equals to 1 and under minus 1 and I to the power 4 equals to 1. We put these values in this expression and we find out that all the even powers and even factorials number became real number, and all the odds power and factorial number is still imaginary number. The two series are now Euler expansion series. Hence from for it written as for cos theta and sin theta, it e to the power x e to the power I x equals to cos x plus I sin theta. Circle, you can see the proof how we use the theta of unit circle where theta is a real number and it measured as a radians. Now we put this formula in polyhedra. For polyhedra are 3D solids shape whose surfaces are flat and edges are straight, for example cube, cuboid and prism and pyramids. For any polyhedron and that does not self-intense. Hence, the number of focus vertices are edged and related to the particular way. Euler formula for polyhedra tells us that the number of vertices and faces together is exactly 2 more than n number of edged. Euler formula for polyhedron can be written as f face s plus vertices minus edged equals to 2. Hence, where f is the number of faces and b is the vertices ss and e is the number of edges.